Okay, so I'll continue from where Amir left off. Okay, so just to recap, we discussed what arithmetic circuits are. We looked at the classes VP and VNP, and the two main players here were the determinant and the permanent. And separating these two is the exercise that Amir gave, and this is what we have been trying to solve for a long time. And then we looked at things that we can do with arithmetic circuits, and something that I think is probably the most important thing is interpolation. And you could think of homogenization as one possible way in which you could use interpolation to do things. And what I'll be talking about in this thing is partial derivatives. So this is going to be the focus of things. So we have an arithmetic circuit, it computes some polynomial, and we would like to now compute some partial derivatives of this polynomial as small arithmetic circuits. So just to see if people were paying enough attention, so let's just say if we have a xn, let's say there are 2n variables, y1 through yn, is easy. By that what I mean is it's computable by a small arithmetic circuit. Can we compute the partial derivative, the nth partial derivative of f with respect to, can we hope to do this efficiently? Maybe we'll move this there. And I think we saw this example some 3-4 times, and the answer should be no, or at least we think it can't be done efficiently. And what's the example for this? This is what we looked at. This is the product of I going from 1 through n, sum j going from 1 through n, yj, xi comma j. And the partial derivative with respect to y1 through yn is precisely just the permanent of this. And if we believe that permanent is hard to compute, then we should not be expecting to compute this efficiently. Okay, good. And what Amir stopped towards the end was trying to say that, okay, we can't compute partial derivatives of this sort, which have many variables in it. But the question we could ask is, okay, can we compute one partial derivative? Let's say I just want to compute dou f by dou xi. Can I compute this partial derivative? Now let me talk about two possible ways in which you could go about trying to do this. And so one approach is very similar to what we did in homogenization. We'll replace every gate with a few copies, where each guy is going to compute something useful about that gate, and we'll somehow try to connect these things together. So let's say answer 1, okay, replace each gate v by, let me just call this v0 and v1. What is this supposed to be? This guy is just a copy of v. Doesn't do anything. But this guy is supposed to be the partial derivative with respect to the variable, what did I choose, xi, of v. And intuitively this is what my circuit is going to be, where every gate every gate has two, I mean, it's now you have a pair of gates for this, one that computes that gate and one that computes the partial derivative. And you just use you just do the normal differentiation. So whenever you have a gate v which was equal to, let's say, u plus w, then you know that, because I'm lazy, let me just call this del I of v. This is del I of u plus del I of w. Great. And if and if v was equal to u times w, then I know that del I of v equals del I of u times w plus del I of w times u. And I have gates that compute each of them, so it lets you build the circuit top down. Great. The other way of doing it is what Amir outlined in the last few minutes, which is that I have some polynomial. Let's say throughout we are interested in the derivative with respect to some specific variable y. This is what we are interested in. Now what I want to do is I want to write this polynomial f as summation y to the I fi of the remaining variables. And by interpolation, we know that by evaluating y at d plus 1 points and taking suitable linear combinations, you have access to every single fi. So you could just write down the partial derivative yourself. I mean, once you extract each of these coefficients, you can just build the partial derivative of f bottom up. Okay, this means that it's not just that you can compute a partial derivative with respect to a single variable. This also tells you that you can compute a partial derivative with respect to y to the I of f can be computed in size order of s times d. So if all you care about is a partial derivative with respect to a single variable, irrespective of how high or what the degree is, you can still do this with just a blow up of d in size. Now the first answer, doing an iterative application of the first answer is not going to, it seems like, so here's an exercise. You could try and answer 2, split each v to, let's say, v0, vi, if you are interested in partial derivative with respect to y to the I. And then I'll let you convince yourself that if you can compute each of the ith order partial derivatives intermediately, then you can build the partial derivative from this. Okay, so what I want to talk about mainly today, it'll still be short, is a really cool trick of Strassen, which would be useful for a lower bound tomorrow. And this is the only lower bound we know for general arithmetic circuits. And so this trick is by Baur and Strassen. And this is a lower bound we are going to see tomorrow, and this will be useful, but let me just state what the lower bound is. If f of x1 through xn equals this really silly polynomial, it's just the sum of the nth powers of xi's, then any arithmetic circuit computing f has, okay, what is the best circuit that computes f? Each x to the n, you can do this by repeated squaring. The number of edges you will need will be like log n, and you can just add up each of the guys. And yeah, and this is the only general arithmetic circuit lower bound we know of till date. And we are hoping that at some point we'll prove EP different from VNP. Things are not that bleak. But one of the key ingredients in Baur-Strassen is the following question, which would be the main thing for this thing, which is that given f as an arithmetic circuit of size S, how small is the circuit computing del 1 of f? Suppose I want to compute all n first order partial derivatives together. So it's going to be an arithmetic circuit which has n output gates. What is the smallest size that I need in order to be able to do that? Okay. So just to recall, if I want to compute just the partial derivative with respect to one variable yi, the size of the new circuit is just order s, because every gate I just doubled and I might have added a few auxiliary gates, but not much. So it's going to be order s. So the very naive thing to do is, like, build the order s circuit for del 1 of f, build the order s circuit for del 2 of f, and so on, and you eventually get a circuit of size order n times f. Baur and Strassen showed that you can actually save in this. Can do with size 5 times s with just a constant factor increase. And this will become very, very important for the Baur-Strassen lower bound that we'll see tomorrow. So I hope the question is clear, what we want to do, and as to why this is not trivial. Instead of n times s. N times s would be the natural way of, it's the naive way of doing it, computing each separately. But Baur and Strassen say that with just a constant factor blow up, you can compute all n partial derivatives together. Okay? No. It's the first order partial derivative with respect to the variable xi. So I'm just using del I. By del I of f, I just mean del f by del xi. That's it. It's just the first order partial derivative with respect to. Okay?
What about the outputs? You need at least n outputs.
Yes. So if the circuit depends on n variables, then it will anyway have n edges. So with just a constant factor blow up. So before we answer this question, here is let's assume that a little bird told us that this was indeed true, and now ask, can we hope to compute all order 2 partial derivatives in order s size? Now this is not fair. Let's say order s plus n squared, because you need n squared outputs. Okay, fine, I'll give you n squared for free. But can you do this with just an order s this thing? Suppose you could. Okay. If yes, then you have a really small circuit for matrix multiplication. An order n squared circuit. If you haven't seen this before, it's a good idea to just think about it for maybe a minute or two. So here's what I wanted. I'm claiming that suppose if it were true that given a size s circuit, you can compute all second order partial derivatives with just an order s blow up, assuming s is more than n squared at least. If you could do this, then this would mean that matrix multiplication of two matrices has a circuit of size just n squared. The reason for this is this. Let's say I want to multiply two matrices A and B. Okay. Look at the following. So I'm just looking at x as a vector of just variables, y is another vector of variables, and I'm taking this, okay? Now, okay, let's call this F. And the claim, it's a simple exercise, is that del ij of F is, okay, so what do I mean by it? So this del xi yj of F is the I comma jth entry of A times B, right? This is just a simple thing to check. Okay, so how small a circuit can I have that computes this? Computing X transpose A, if this guy is an n cross n matrix, this is an order n squared size circuit. Computing By is an order n squared size circuit, and then now I'm taking an inner product. So it's an order n squared size circuit. If this question were true, then this will mean that there is a circuit that computes all the partial derivatives in just order n squared. But that would mean that you are actually computing every entry of A times B in a circuit of order n squared. I mean, it's not that this says this is false, but it'll be awesome. But we don't know if it's true yet.
So the line name would be order S times n.
Yes.
Can we even do S times n to the point 9?
I don't think it is known. Yeah, anything better than S times n is not known. Okay, is that?
S times n squared?
No, like you could compute all second order derivatives in S times n.
So you compute all first order derivatives with this, and then you now compute all the. Yeah.
Is it known how to do the order S plus matrix multiplication?
No, even that is not known. I think. Yeah. Anyway, so hopefully this question makes this more surprising. I hope. Yeah. Okay, so we'll see a proof of this. So one thing, this proof is it's very good if one can draw pictures. I think I can draw pictures better on PDFs than on board. So on the WACT program page, there are sort of chapters from the 2 surveys for each of the bootcamp lectures. And I mean, I'll attempt to draw a picture, but it'll still not be that great. Okay. So let's see the proof of Baur-Strassen. So here's what we're going to do. So the natural thing to do when we are looking at partial derivatives is to try a top-down approach. And somehow for the Baur-Strassen trick, that doesn't work. I mean, it's not clear how to make it work. So Baur-Strassen do this really nice thing. So which is, they start with, so let's say this is my circuit for F. Somewhere in the bottom, there is going to be a gate, either a plus gate or a multiplication gate, that has 2 inputs, let's say x1 and x2. Okay? Now this could either be a plus gate or a times gate. Okay? From here, we are going to first go to a different circuit where I'm going to replace this by a new variable y. Okay? So if this had s edges, then this guy has at most s minus 2 edges, because I just got rid of 2 of them. Okay? And I'm going to assume by induction that this guy, I should call this f prime. There is a multi-output circuit for f prime. Now this is going to have y x1 through xn. Like this is del y of f and del 1 of f2, del n of f prime. That computes this in size at most 5 times s minus 2. That's the induction hypothesis, because this is a smaller thing. And using this circuit, I'm going to build a circuit for f, the multi-output circuit for f. And I'm going to do this by adding just 10 more gates. 10 more edges. Okay? The easiest thing to do right now would have been to draw the actual things. I think it'll get messier, but if you want to see the actual picture, look at the survey. So, or as Jaikumar once said, if it doesn't work for 10, it'll work for larger values of 10. So, so let's just see what happens. And so what do I know? I know that f equals f prime, where I replace the variable y, by x, whatever that operation was, y. So this is what. So this is the relation between the polynomial f prime and the polynomial f. Thank you. Right. So now, good. So now suppose I want to compute the partial derivative with respect to variable x7 of f. How does that relate to the partial derivatives of f prime? Now this is nothing but the partial derivative of f prime with respect to 7, but then after that you have to set y equals x1 circle x2. Right? So this is what the picture is going to be. There was some variable y here. I'm going to replace this by x1 and x2. So let me just call, so this is supposed to be the derivative with respect to x1, this is supposed to be derivative with respect to x2, and these are the rest. And so far we have handled these guys. Is this clear? Okay. So 7 is just an arbitrary variable that is not 1 or 2. So as far as it is not 1 or 2, the derivative of f prime with respect to the 7th variable is, or rather the derivative of f with respect to the 7th variable is the derivative of f prime with the appropriate substitution. Okay, I'm just applying chain rule, that's all. Okay, so now, let's look at the two cases. The case is like y equals x1 plus x2. In this case, what is going to be the derivative of f with respect to the first variable? So this is just a simple exercise where maybe I should keep calling it x1. Okay, derivative with respect to x1 of f prime evaluated at y equals x1 plus x2. Plus I now need to differentiate, I now need to differentiate, look at the derivative of f prime with respect to v, or with respect to y, and then differentiate y with respect to this, right? Plus with respect to y, and derivative of y with respect to this is just 1. So you again replace y equals x1 plus x2. Right? So this is the expression for the derivative of f with respect to this guy. Where did I put that? Okay. Okay. So now the other thing that needs to be checked is, like, suppose y equals x1 times x2. Then the derivative of f with respect to x1 equals the derivative of f prime with respect to x1 plus derivative of f prime with respect to y at y equals v1 times v2 times, in this case it will be x2. x1 times x2, because the derivative of x1 x2 with respect to x1 is x2. Right? So this just says that, taking the outputs of these guys and taking some more products here and there, you can sort of build the n outputs of f that you need. Now, even if you don't believe me that the number of extra edges that you're going to add is going to be 10, even if you think it was 20 or something, you have to appropriately adjust this constant. So, but this basically just means that this takes 5 times s minus 2 plus 10 edges with the appropriate additions. And that just proves this by induction. Okay? So this is more or less the Baur-Strassen thing, and so there are various other derivatives that are used often in arithmetic circuits, especially in depth reduction and so on. And I don't know how much of details I want to get into with respect to VSBR, but one other case, so this is a special example where you chose a node that was very, very deep down in the tree, or very deep down in the circuit, and you're taking a derivative with respect to that node in some sense. But you could, in general, sort of just take an arbitrary node in the tree and cut off its edges and call it a new variable y, and then say, okay, now I'm going to look at derivatives of this. And such gate derivatives will turn out to be very crucial in depth reduction. Now, in the next lecture or something, so when we are doing depth reduction, I probably won't be going into the VSBR proof, but I think people who have not seen the depth reduction, you should look at the surveys of Amir or the other survey. They're two very similar looking proofs. They're more or less the same proofs, but written in two different ways to understand the same sort of derivative. Okay, so since
the depth reduction, you said you are going to use the partial derivative via node, or you're going to use another?
So okay, so what would happen here is that you will sort of relabel one of the internal nodes of your circuit by a new variable. You will just cut the two inputs that feed into it, and you will just call it a new variable. Now the resulting polynomial is going to be some polynomial on the other variables plus this guy.
Yeah, I know. I read the reduction. I didn't understand. You said there are two options.
So there is the original proof of VSBR, Valiansky, Berkowitz, and Rakov, they do something like a gate derivative, but it's in a slightly different language. The exact way of doing it in a gate derivative is in the survey of Amir Shpilka and Amir Yehudeev. And that, okay. I clearly have a lot of time, so let me just give maybe a trailer to what happens in Baur-Strassen. Why is this useful for proving lower bounds? And so what would eventually end up happening is something along the lines of, I want to compute this polynomial. The set of all derivatives of this is something that looks like x1 to the n minus 1 to x1 to the n minus 1. Sorry, xn to the n minus 1 or something. And maybe I shouldn't be getting into this right now. Okay, since I clearly have a lot of time, I'm going to start doing the depth reduction part right away, so if that's okay. Okay, so let's start with the depth reduction for formulas. Okay, and so here is a theorem. If f is computable size S formula, then f is computable by a size S, poly in S, depth order log S. Okay, so this would be so this is sometimes called Spira's lemma, or it's attributed to Brent. The proof is neat, and it gives So the proof is as follows. So we have a circuit, we have a formula which is possibly very imbalanced. And because we are working with addition and multiplication gates, we'll always make sure that the right child of any gate is heavier than the left child in terms of the size. So at every gate, we just twist the gate accordingly to make sure that the right side is heavier. Okay? Now, for each node in the circuit, you can just look at what is the size of the subtree under me. To begin with, it's S. What I'm going to do is I'm going to start walking down the rightmost path and look at the first point where I drop below, let's say, 2/3 of S. So this guy is less than 2/3 of S. Okay? I start off with S, I'm going to walk down the tree until the subtree becomes smaller than 2/3 of S. So I'm at some node V. What can I say about the subtree under V? I want to claim that the size of the subtree under V must be substantial. The first time you drop below 2/3, you can't drop drastically. Why is that? Because the circuit is right heavy. Point is, if the parent of this guy, let's say whatever this V prime is, I didn't choose V prime because V prime had size more than 2/3. But now I went to the right child of V prime. And because the right child is heavier, it must have at least 1/3 of the nodes. Okay, so therefore, you can find a node V such that the size of the subtree at V is strictly less than 2/3 of S, but is at least S by 3. This is what you have. Okay? So now we'll take the derivative with respect to that gate. What does that mean? I'm just saying that this guy will have two inputs. I'm going to erase them. I'm going to call V a new variable. Okay? Now, the original polynomial f will be some new polynomial, some f prime in the x variables and this variable v. Maybe I should call this y just to keep the notation. Okay, this is some node v that we picked up. I'm going to replace v by a variable y there. Okay. So the polynomial f prime is now polynomial f prime is something in the variables x and the variable y. And the relation between the original polynomial f and the new polynomial f prime is that f prime equals f of x, and by this what I mean is the polynomial computed by the node v. So if I plug in that polynomial there, I should get back my f prime, because this is what the circuit was computing anyway. Okay? But because we are dealing with a formula, the variable y occurs at just that one point. That's the only place that the variable y occurs. So this f prime is not just an arbitrary polynomial, but it's something that looks like a times y plus b. The degree of y has to be 1 because this is the only place that the variable y occurs in. Okay? So now the natural thing to do is, if I can somehow compute the two polynomials a and b, I can just compute f prime accordingly. Okay? Now great. So what do I know right now? I have basically cut the node at v. So therefore I know that size of f prime, this is at most 2/3 of s and at least 1/3 of s. Right? This is what I know. Oh, sorry. Yeah, sorry. 1/3 of s and 2/3 of s. Okay. Now what do I know about b? Now b is nothing but f prime of x comma 0. Because if I substitute y here, I get 0. And a is going to be f prime of x at 1 minus f prime of x at 0. Right? So this means that this is computable in size something like 2s by 3. I mean, it's just an upper bound. This is also the same thing. And from these two, you can just build the circuit for f. What do you do for that? suppose you have a box that computes f prime of 0, f prime of 1. Let's say you have another box that computes f prime of 0. This is a box that computes A, right? And I'm supposed to multiply this with the node computed at V. And now I'm going to, I have to add f prime of 0. Okay? Okay, yes. So let's say this is -1 and this is, yes. Okay? And what do I know from this? This is a constant, okay? But this is computable by a size 2s by 3 circuit. This is computable by a size 2s by 3 circuit. Every box here is computable by a size 2s by 3 circuit. So therefore, the overall size, so the depth reduction that I'm going to get is going to be, if this becomes poly, and so I have the total size of my new circuit is going to be bounded by 4 times the recursive things that I'm going to get here. But the point is the depth is only increasing by a constant factor. I mean by an additive constant. Okay, so what I'm moving around. What I want to say is that the size of depth reduction, size of S, is bounded by 4 times the size of 2s by 3. By this, what I mean is, what is the size that I get when I depth reduce a formula of size 2s by 3? And I need to multiply that by 4. But the depth of S is going to be bounded by at most depth of 2s by 3 plus something like 2. So if I recursively keep computing this depth reduction on each of those boxes, I end up with a circuit of depth about order log S, but size is just polynomial in S. I end up with a formula of depth order log S and size polynomial in S. Okay. Now, I just want to point out one thing which will end up being useful in some lower bounds later, is that finding a node of intermediate value, like something like S by 3, 2s by 3 or something. In this case, we chose it based on size. But this is a very, very general statement that you could make. Like, think of the case where, let's say the degree of the guy here was D. Then the same trick will also tell you that you can find a node whose degree is at least D by 3 and at most 2D by 3. Now you could also do the same thing for various other potential functions you could look at. The only thing that was used here was that whatever the potential function here is lower bounded by the sum of the values of its children. So that's the only thing you needed for this. And there are various avatars in which you can see a similar sort of reduction. Like, for example, if you start off with a formula that is homogeneous, what you end up here is also going to be homogeneous, where you know that every multiplication gate, the children here will have degree something like 2D by 3. So when I start with the multiplication gate and look at its children, the degree has dropped by a constant factor. So the various other structural results that you could get from this. So let me give you one. It's not really a depth reduction, but it's a structural result which will turn out to be pretty useful. And how much time do I have? 10 minutes. So let's say F is computable by a size S homogeneous formula. What this means is that every internal gate computes a homogeneous polynomial, and say degree of F equal to D. Okay. Then there is an expression of the following form for f. I equals 1 through s, where gi1, gir. Rather than, I will write it down shortly, but let me tell you what you get out of these gijs. 1 through s. So if the degree of f here is d, now we'll turn out the degree of g is like something between s by 3 and d by 3 and 2d by 3. And the degree of the next guy will drop again by a factor of 1/3 or 2/3. So it's a product of guys where the degree of every successive factor is dropping by a factor of, it's sort of geometrically decreasing. And the number of summons is just s. Now because the factors are geometrically decreasing, r will turn out to be something like log d. So this is also called a log product decomposition. Okay, and we'll just see the proof of this and stop, and there'll be variants of this which will be useful in the depth reduction, the next thing.
Can you repeat what is
So what I mean by this is that there is a way in which, so think of it this, I know that f is computable by homogeneous formula of size s, and its degree is d. If somebody allows me to compute polynomials of degree something like 2d by 3, I give them to you for free, then there is a decomposition of this sort where each of the degrees sort of drop down by a constant factor. So I'm just saying that there are s summons. F can be written as a sum of s terms, where each term is a product of log d guys, where the degrees are geometrically decreasing. So, right, r may depend on I. So degree of gij is less than or equal to 2/3 par j of d, and at least j of d. So this is the sort of term that you get. And because of this, each ri is going to be order log d. Sorry?
I thought these are two indexes. I didn't know it's a subscript I1.
Yeah. So each term factors as a product of log d terms of smaller degrees. So this will turn out to be interesting in the sense that one way to depth reduce a circuit is we'll eventually want to show that every circuit can be written as a depth 4 circuit. So if you're computing a degree d polynomial, the depth 4 circuit will be something that looks like there is a big sum gate on top, and then there is a bunch of products, and then there's another sum, and there's a bunch of products. These GIJs will be what are computed here. And I'm going to be multiplying a few of them and then adding them together. Right now what this says is that this summand is S, and these degrees are something like 2d by 3. That's the bound that you've got so far. This is not interesting yet, but it will soon be interesting once you push this further down. Okay, so this was the motivation for this. And yeah. I mean, it's the fact that each of these GIJs are, the degree of each GIJ is a constant factor away from the polynomials that you were computing. And that is what makes this not trivial. And so the proof is exactly along those lines, where the node V we are going to find is not going to be a node where the size is between s by 3 and 2s by 3, but instead the degree is going to be between s by 3 and 2s by 3. Okay? So we'll again write it as f equals a times phi v plus b, where degree of phi v is between 2d by 3 and d by 3. Okay? Now, because f is a homogeneous polynomial of degree d, this guy is a homogeneous polynomial of degree between d by 3 and 2d by 3. This means that a is a homogeneous polynomial of degree between d by 3 and 2d by 3, because they should add up to this thing. Great. Now, what we are going to do is this is going to play the role of G11. I've extracted one guy from this summon, and I'm going to do induction on these two guys. I just want to make sure that I can do induction. Okay? So let's just go back to this picture and see what phi v and so if I had some formula and I found a node v here, which I erased, then if the size of phi v is, let's call this S1, that's the size of the subtree under V. What do I know about B? Now B was nothing but I took this formula, I just cut this off and set this to 0. So all that B is like, you're just taking the formula for f and just removing the subtree under V. Okay? So what you know right now is that you know that size of phi v plus size of B is at most S. Right? Because these are two disjoint parts of your formula. Phi v was the subtree under V, and B is everything else but that. Right? Now, therefore, I can apply induction on phi v and on B. What will it tell me? So by induction, it will tell me that B can be written as summation I going from 1 through S1. I'm going to relabel them and call it GI2 to something, plus something I going from 1 through S2 of similarly GI1. And you can just, because G1 was of the right degree and whatever you're left with is also of the right degree, the induction just tells you that once you expand this out, you're going to get a term as claimed in this product, in this decomposition. Yeah. Even if it's less than or equal to, it's fine, right? I mean, at the base case, you need to do something, that's it.
What is the size of phi v is? Size of phi v is S.
Sorry?
You need, for induction, you need the size of G and the size of phi v, both of them are strictly.
Yeah, but I'm removing a non-trivial part of the tree because I found a node that has intermediate complexity. I'm removing something, I'm removing some part of my subtree. Right? Okay, so maybe here is something to think about, and we'll get back to this in the next thing to do when we are doing depth reducing it further.
Is B homogeneous?
Yeah, B will also be homogeneous.
If you replace B by 0, what happens then?
So it will, I mean, any all monomials where it was,
Okay.
yeah.
Okay, I have a question.
Huh.
So over there, in the loose negation, right, even though the original thing was monotone,
Uh-huh.
loose negation, something wrong when you insist of obtaining monotone balance formula?
Yes, it is. And I'm going to, I mean, that was one of the exercises. The negation was to just figure out what A is, right? I mean, that's why I needed the negation, the subtraction here. So the question I wanted to ask, let's just think about it. Like suppose F is written as A times phi of V plus B, where V is some internal node. Can you look at the formula and figure out what A is supposed to be? I mean, that is one way of figuring out what A is. You evaluate that F prime at 1, evaluate F prime at 0, and subtract the 2. But you should be able to look at the formula and just figure out what A should be. So this is perhaps a good point to stop, and we'll get back to this point in the next. Okay, so I found a node V whose degree was between 2d by 3 and d by 3. And f was a polynomial of degree d. So therefore, G11 must be a polynomial of degree something like 2d by 3 and d by 3. Right? That was the claim here. The first guy had to be between 2d by 3 and d by 3. Now I do induction on the remaining guys. Whatever is that degree, it's upper bounded by 2d by 3 of what I started off with, and lower bounded by d by 3. So in the induction hypothesis, I might be adding additional factors of 2d by 3 and d by 3. But that's about it. So the degrees are geometrically going down. Okay. Okay, so we'll start with something like the log product decomposition and then push this down to depth 4 and show that there are efficient circuits.